Okay, I'm going to try to get all of the multiple choice ones from that review done in one go. So it's 1 through 8, multiple choice section. First one, it asks what would be the weight of an object that's pulling a spring down. So we know the spring has a K, or a spring constant, of 200 newtons per meter. And we know the distance that it's getting pulled down is 0.2 meters. So we know then these two pieces of information. Well, first thing we need to know is this. Remember, this is from, we're going to need this formula. We talked about it briefly, but we need this formula because the force that you are holding a spring with is the force that the spring would be exerting back the other direction. So in this case, we have this weight held on the end. It's exerting a force due to gravity, and since it's in equilibrium, the force of gravity on that object, or the object's weight, is equal to the spring force. So don't forget that the force of gravity is equal to the object's weight. So what we can say then is that Kx equals the weight of the object. And so K is 200 newtons divided by meter. The X is this 0.2 meters that it's hanging down. So this right here is X. So 200 times 0.2 gives us 40 newtons, I believe. No, sorry. Yeah, 40 newtons. My bad. And that should be the weight of that object. Alright, number 2. So it talks about all this stuff with the spring. The main thing we need to know here is that X on the first one, it was originally at 0.10 meters, now it's at 0.5 meters, or sorry, 0.15 meters. So that means X1 is 0.05, and X2 is equal to 0.1 meters, because it's at 0.2 meters. So we now know that X1 is at 0.05 meters, and X2 is at 0.1 meters. And it's asking us to figure out what is the spring's potential energy at A compared to B. Well, on this case, what we're going to do is we're going to do EPE, and I'm just going to plug in ones like we've done several times before. 1/2 times 1 times 1 squared. And this 1 will be connected to here. So it'll be EPE is equal to 1/2, right? This is for our first scenario. For the second one, EPE2, 1/2 times 1. Now, these two numbers, you should clearly see, 0.1 meters is double of 0.05 meters. So instead of 1, I'm going to plug in 2 squared. So I should get EPE2 equals 1/2 times 4, or 2. Well, 2 is 4 times greater than 1/2, so the answer is 4 times greater. Alright, number 3. Alright, so it's asking for what would the graph of kinetic energy to velocity look like. And I ask you, if this is a formula, if we converted this to y and x, and I made KEY, and then just made up a number for m, and put x in place of v, what would it look like? Well, of course it would look like a parabola. So that means this looks like a parabola. That's 3. 4, same thing. Elastic potential energy equals 1/2 kx squared. And so, it should be a parabola as well. Alright, number 5. The diagram represents a frictionless track. A 10 kilogram block starts from rest at point A and slides along the track. The block moves from point A to point B. Don't get tricked. It's not talking about point C. It says point B. So at point B, for those of y'all that don't have it, this is what it looks like. Point C is 2 meters above the ground. B is at the ground. And A is 5 meters above the ground. So, if it asks how much potential energy did it change, it says the total amount of gravitational potential energy changed to kinetic energy. Well, if it's from A to B, we know that all of it changed. So gravitational potential energy all changed to kinetic energy. So that means that mgh would tell us the amount changed to kinetic energy, and that is 10 times 10 times 5, or 500 joules. Okay, so that's 5. Number 6, 20 Newton block is at rest at the bottom of the frictionless incline as shown. It's shown like this, 3, 4. Okay, obviously this would be a 5. How much friction how much work must be done against gravity to move the block to the top of the incline? Well, the first thing we need to remember is that these two numbers don't matter, because it's only the distance that you're moving in the direction that the force is being applied. And so since the force of gravity is pulling down this way, we're having to do work this way, which means that we're only worried about the distance in this direction. And these two distances in the x direction and in the diagonal direction mean nothing to us. So we're worried about this, and we're worried about the force of gravity on that object, which is equal to mass times 10. But luckily, we already know that the force of gravity is 20 newtons. It's already given to us. So work is equal to the force of gravity times distance, and work would be equal to 20 times 3, and work should be equal to 60 newtons. Or sorry, not newtons, 60 joules. Let me rewrite that. 60 joules. Alright, that's 6, 7. The diagram shows a 1 times 10 to the third Newton crate to be lifted at a constant speed from the ground to a loading dock 1.5 meters high in 5 seconds. What power is required to lift the crate? Okay, so power is equal to work divided by time. Work is equal to force times distance. So I know that the force is equal to 1,000 newtons. That's what 1 times 10 to the third is. And I also know that distance is equal to 1.5 meters. And I know the time is equal to 5 seconds. So the first thing I'm going to do is I'm going to figure out what work is. Work is equal to 1,000 times 1.5, which of course is 1,500. And then I need to find power. Power is equal to 1,500 joules divided by 5 seconds, or power is equal to 300 watts, which would be 3 times 10 to the second for you non-scientifically notation inclined. Alright, then the last one. Which object would require no work to be done? The answer is D, because if you're holding an object stationary, the change in displacement would be equal to 0, and work is equal to force times displacement. So if this is 0, then there is no work being done. Alright, and that is the answer to the multiple